Section 6.4, identifying functions. So we're going to look at all four types of functions just like we have been doing. And we've kind of looked at how they move, transformation, shift left, shift right, stretch and shrink, or compress. And we've looked at the equations some already, and the graphs some already. So really we just have to focus on tables here. The rest of this should really be review. Okay, so talking about linear, we know that a linear function looks like this. We have a graph that's just a straight line. Either going, if the slope is positive, it's going to be going up. If it's negative, it'll be going down. And we know that the equation has no exponents. It looks like y equals mx plus b. So here we have y equals 3x plus 2. Now, it doesn't always start out y equals. Sometimes we have to solve it to get it that way. So we could also have like 3x minus 2y equals 8. That's still linear. Okay, that's still just a line. Remember, we also have our special cases like x equals 2 or y equals 4, horizontal and vertical lines. Those are linear too. Okay? But the key is that linear doesn't have absolute value bars and it doesn't have an exponent. So all of these are examples of linear equations. Now, to look at a table, x is increasing at a constant rate and y increases at a constant rate. So look at how much you think we talk about slope, it's change in y over change in x. Well, that means the change has to be consistent. So looking here, from the first one to the second one, it's going down 1. From the second one to the third one, also going down 1. Now checking this side, that's going down 3. And from negative 10 to negative 13 is negative 3. So x is constantly changing by the same amount, and y is constantly changing by the same amount. Okay, that's what creates our slope, our change in y over our change in x. Now, we can look at a function map the exact same way. If the lines are not going straight across, if they're all crazy, we can rewrite it as a table. This is really this exact table made into a map. Negative 3 goes with negative 7. Negative 4 goes to negative 10. Negative 5 goes to negative 13. So anytime you see this, just go ahead and write it as a table, and then do the exact same thing we did here. Check to see if the change in x and change in y is consistent. Okay, and then of course we talked about the graph is just a straight line for linear. Then for quadratic, that's the next one we did. That's the U-shaped graph. And that means we have an x squared. It has to have an x squared. If it doesn't have an x squared, it's not quadratic. Okay? It could have that middle term, so it could be like y equals negative 5x squared plus 2x plus 4 or something. Or like this one just has the x squared. It doesn't have the x term. It's still quadratic as long as it has an x squared. Then, if x is increasing at a constant rate, but the second differences are consistent. So x goes up by a constant rate. Look, we're going down 1, down 1. But y does not. So from 12 to 19, that's 7. From 19 to 28, that's 9. And then we actually need to add an ordered pair here. So the next one down would be negative 6 and 39. Just to see what's going on here. So here that's 11, difference of 11. Then the second difference is from 7 to 9, that's 2. From 9 to 11, that's 2, if those are the same. So if you have to do this twice before they match, then it's quadratic. So first differences are the same, it's linear. Second differences are the same, it's quadratic. Sometimes you can see your vertex, and we looked at that when we looked at the tables. But sometimes like this, you can't see the actual vertex. This is either points before the vertex or after the vertex. So sometimes you have to be able to find the second difference to see if they're the same. Once again, this function map is the exact same as this table. So if you can do the table, you can do the function map. Just rewrite it as a table if you need to. All right, looking at the next one. We have exponential. So exponential, remember you can have exponential growth or decay. Remember growth is going up and decay is going down. So can have growth, or we can have decay. Okay, and you are always going to have an x in the exponent. It has to be something to the power of x to be exponential. And it always looks like an L shape. Now looking at the table, it says x increases at a constant rate, but y increases by a common factor. What that means is by multiplication or division. By multiplication or division. So here we're going up 1, up 1. But over here, this is times 2. This is times 2. And the same thing here. This map is just this table written as a map. 3 goes to 8. 3 goes to 8. 4 goes to 16. 4 goes with 16. 5 goes with 32. 5 goes with 32. So it's the exact same thing. Okay, so if your y's are changing by multiplication or division, it's growing or decaying exponentially. It's an exponential function. And the last one we talked about was absolute value. Remember, always looks like a V. Okay, always makes that V shape. Always has these bars. If you don't have the absolute value bars, it's not absolute value. And this, as x increases at a constant rate, y increases at a constant rate, but we'll have a vertex. Okay, so this does go down 1, down 1. This is going up 1, but if you were to graph the whole thing, it should have a point. Okay, if it doesn't have a point, then it's not absolute value. It has to make that V shape. But it should make sense that it's linear in nature, is that it's increasing at the same rate. Because this looks like just a straight line on this side. This looks like just a straight line on that side, so you just have to make sure you graph enough points to see whether or not you have a vertex. Make sure you look at your table, look to see if it repeats. Look to see if on the other side of this perhaps you have negative 2, 1 and negative 1, 2. Do the y values repeat? That's how you find your vertex. Okay. If all else fails, graph it in your graphing calculator. If you're given a function and you're not sure. But remember, if it has these bars, it's going to be shaped like a V. Remember we talked about like the minus 3 here shifts it down 3. So you should have a rough idea of what this is going to look like. Alright, just a little bit more here. Okay, we're going to identify each function as linear, quadratic, exponential, or absolute value. Now when I want you to show me this, I want you to kind of give me some evidence here. So this one right here, it has an x with no exponent. So x with no exponent. So that is linear. Okay, don't just tell me linear, tell me why. Okay, this one is exponential. So we're going to say L-shaped. That makes it exponential. Now we get to the tables and the maps, so I have to be a little bit careful. So here, that's going down 1, down 1. Here, from 12 to 19, that's 7. From 19 to 28, oh, this is the same one from our example. That goes up 9, and then I would always give you at least 3 if it happens to be quadratic, so that we can see that this is 11. So those common differences are the same, 2 and 2, so it's quadratic. So showing me this, showing me those second differences, that is your work. I need to see work on tables. Okay. And then here, I'm just going to set up an XY table. Negative 3 goes to negative 2. Negative 2 goes to 0. And negative 1 goes to negative 2. Okay, so it looks like it's either quadratic or absolute value because I can see a vertex that repeats on the other side. So now it's up to see if it's consistent or if I have to go to the second differences. So here, it's changing by 1. But over here, that's changing by 2. And that's changing by 2. So it's consistent. So this is absolute value. And that's all there is to it. Go ahead and get started on your practice. You are doing all of the new and all of the review this time. These should go pretty quick. Let me know if you need any help.